So hello everyone, welcome back to the channel Code with AKJ, and today is day 61 of solving LeetCode 75 challenge. And today we are going to solve one of the most famous dynamic programming problems, that is house robber. So before we begin, if you are enjoying this LeetCode 75 series, make sure to like this video, comment your approach or any doubts below. Share this video with your friends preparing for coding interviews and subscribe to the channel so you never miss the upcoming videos in this complete LeetCode 75 challenge. So let's move to the problem statement. The problem statement says you are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. So let's understand this problem. So we have a street containing several houses, and each house contains some money. So 1, 2, 3, 1, these are the amount of money each house consists of. But there's one condition. So if you rob two adjacent houses, the police will immediately be alerted. And our goal here is to maximize the amount of money that we can rob. So let's understand with these two examples. So here I have written two examples, example 1 and example 2. So these are the index values 0, 1, 2 and 3, and these are the amount of money each house contains, that is 1, 2, 3 and 1. So the condition here is no two adjacent houses can be robbed at a time. So if suppose we have robbed this particular house 1 which contains money 1, we cannot rob the second house adjacent to it, which is 2. So suppose if we rob the house 1 which contains value 1, the total amount we currently have will be 1. And then since we cannot rob the adjacent house, we'll move to the house 3 which contains value 3. So our total amount would be 4. And again from here, since there are no houses in this particular street, we'll stop here, and our maximum amount in this case would be 4. And suppose if we start robbing from house 2 which contains amount 2, our current amount would be 2, and then we'll move to the house 4 which contains amount 1, and our total value would become 3. The amount we got after checking these two conditions are 4 and 3, and out of these 4 and 3, maximum we can collect is 4. So the best way to rob this street of houses without alerting the police is the first condition, which is robbing the house 1 and then robbing the house 3, which will get us the maximum amount of money, which is 4. So in the same way, let's try to check with this second example what will be the maximum amount we can collect from this street of houses without alerting the police. So if we start from house 1 which contains value 2, the current value would be 2, and then we cannot rob the adjacent house, so we'll move to the house 3. So house 3 has money 9, and our current amount would be 2 plus 9, which would be 11. And again we cannot rob the adjacent house, so we'll move from 9 to 1. So house 5 contains amount value 1, so our total value collected would be 12. So this would be the first case. So in the same way, if we start from index 1 which is house 2, our value would be 7. So the current amount we have collected would be 7, and we cannot rob the adjacent one, so we'll move to the third amount value which is house 4 which contains rupees 3. So our total collection would be 7 plus 3 would be 10, and since we cannot move to the last house, so we'll stop here. So again we got two conditions and two separate amounts, which is 12 and 10, and the maximum amount of these two is 12. So hence this would be the optimal way of robbing these houses, which is we'll start from house 1 and then we'll move to house 3 and then we'll move to house 5. So for the second example, the maximum amount we can collect here is 12. So here you can observe that for every index I, there are two options here, which is to rob this house or either to skip this house. So if we try to rob this house, the condition here would be that we'll collect this amount of money in our total value, and then we'll move on to the I plus 2 house, and we can either skip this particular amount of value and we'll start with the second house. We'll get a certain amount for this particular condition and a certain amount by skipping this current house, and we'll compare these two amounts and we'll take the maximum out of it. So this is all about this problem statement. So whenever we find this particular pattern that for every index I will have either two choices to select to solve this particular problem, this generally redirects us to dynamic programming algorithms. So the final recurrence relation for our problem here is that solve of I would be max of n of I plus solve of I plus 2, comma solve of I plus 1. So here's the code for our recursive solution where we have taken the size of our nums array and we have called solverec function by sending the index which will be starting from our first index 0, and our base case here would be that if our index crosses this street value which is our nums array, then we'll return 0. And for every index we know that there are two options here, which is either to rob or skip. We'll take the maximum out of these two calculations. So the rob would take the current value and we'll move on to the index plus 2 since we cannot move to adjacent house to rob. And the second condition here is not rob or skip. We'll just move on to the next index. So finally we'll return the maximum value of rob and not rob, which will give us the maximum amount of money we can rob without alerting the police. So let's quickly run this code. So it's working, so let's submit. As you can see, this approach gives us time limit exceeded because this is a recursive solution and we are repeatedly calling the same function again and again, which generally makes time complexity exponential. So we'll understand with our recursive tree and we'll try to reduce that time complexity and make it linear. So the time complexity of our recursive solution was O of 2 power n, and the space complexity was O of n because of recursive stack. So why we got TLE? Because we were calculating the same state again and again, which generally gave us the exponential time complexity. So you can see that with this particular recursive tree, here we can see that same state is being calculated again and again, which is S of 2 in this case, or S of 3 as well as S of 4. These cases are being repeated again and again, so because of this, our time complexity got exponential. So to overcome this particular problem, and since the same indices are solved repeatedly, we'll try to restore this answer. And for that, we'll be using a better approach called memoization, where we'll try to create a DP array and we'll try to store each and every state's value inside that particular array. And whenever we'll find that same state is being called again, we'll directly return that particular value from the array. And if it is a new state which is being calculated, then we'll try to calculate that particular state. So whenever solve of I is being called, we'll first check in our DP array. So if it is present, then we'll directly return the value from our DP array. And if not, we'll calculate it and we'll store it in our DP array. So in this way, each and every state is being called once, and same indices will not be solved repeatedly. So in this way, our time complexity will be optimized from exponential to linear, which is O of n. And the space complexity remains same, O of n, since we are using recursion with extra space O of n because we are storing each and every state's value inside our DP array. So let's quickly code this approach as well and let's submit. So here's the code for our memoization approach, where we'll be creating a new DP array which will store the values of each and every state which is being calculated. The initial values of all those states value would be -1, just to track whether it is being calculated or not. And the code for our solve memo function would remain same. That is, we have two choices for every index, which is either to rob or not rob. We'll be calling this DP array for each and every call, and we'll first check whether this index is being calculated and stored in our DP array or not. With this particular condition, that is DP of this particular current index is not equals to -1. It means this state has been calculated already. So we'll directly return the value of DP of current index. And if not, we'll store the DP of index, which is the current house value, by taking the maximum of these two choices, which is rob or not rob. And the base case remains same, that is, if this index goes out of bound, then we'll return 0. So the time complexity of this approach is O of n, and the space complexity of this approach is also O of n. So let's quickly run this code. It's working, so let's submit. As you can see, this approach gives us successful submission. So till now we have used two approaches which generally used recursion, but in this approach, let's try to remove recursion completely. So we'll build the answer from the end where dp of I is nothing but the maximum money that can be robbed starting from the house I. So since the maximum amount of this particular index I is dependent on these two states, let's try to create this array with size n plus 2, and we'll initialize this array initially with 0. So our recurrence relation will update to dp of I is equals to max of the nums of I plus dp of I plus 2, comma dp of I plus 1. So this would be our current recurrence relation, which is dp of I would be the maximum value of nums of I plus dp of I plus 2, comma dp of I plus 1. So let's try to do a dry run on this given example first, and then we'll try to code this approach and we'll discuss the time and space complexity. So now let's do a quick dry run. So we'll start from the last index. So we are here. So dp of I is maximum of n of I plus dp of I plus 2, comma dp of I plus 1. So this is the dp of I here for the last index. So if we rob this, the value would be 1 plus dp of I plus 2 is 0, which is 1. So if we skip this, the value would be 0, which is 0. So we'll take the maximum out of it, which gives us 1. So dp of this value will update it to 1. So now we'll move to the next index, which is 3. So again, we'll calculate with this given recurrence relation, which is n of I plus dp of I plus 2. So n of I here is 3 if we rob, plus dp of I plus 2 is 0, which gives us 3. And if we skip this particular index, the value would be dp of I plus 1, which is 1. So the maximum out of it is 3. So this will get updated to 3. So we'll move to the next index, which is 9 here. If we rob this particular house, then the value would be 9 plus dp of I plus 2. So here the dp of I plus 2 is 1, which is 10. And if we skip this house, then the value would be dp of I plus 1, which is 3. So we have two values and the maximum out of this is 10. So we'll store this particular index with 10. Again, we'll move to the next index. Again, we'll take two choices. So if we rob this, then the value would be 7 plus dp of I plus 2. So here the dp of I plus 2 is 3, which gives us 10. And if we skip this, our value would be dp of I plus 1, which is 10. So the maximum out of these two is 10. So we'll store this value with 10. Again, we'll move to the next index. Here value is 2. So if we rob this, then the value would be 2 plus dp of I plus 2, which is 10, which gives us 12. And if we skip this house, then the value would be dp of I plus 1, which is 10 here. So the maximum out of these two would be 12. So we'll store this dp index with 12. And we'll move to the next index. So here we can see that we have moved out of the bound, and after finishing this calculation, we will return dp of 0, which generally gives us the maximum amount of money we can rob without alerting the police. So in this case, our answer would be 12. So 12 is the answer for our second example. So in this way, we will try to create a dp array. We have calculated each state only once and there is no repetitive calculations. And the time complexity of this approach here would be O of n, and the space complexity here would be O of n. And this O of n is because of the dp array we are using to store the values. And we have removed the recursive stack completely. So this is the tabulation method, and let's try to code this approach. So here's the code for a tabulation approach. The code remains almost the same, and we are using the dp array. We are trying to build this array, and we'll start from the last index. So to calculate rob nums of I plus dp of I plus 2, and to skip, the value would be dp of I plus 1. And for every state, we'll store our dp array with max of these two choices, and at the end we'll return dp of 0. So let's run this code. It's working, so let's submit. So this also gives us successful submission. Let's move on to the next approach, where we'll try to optimize our space complexity and will not use any external space to store the values of each and every state, and we'll try to make our space complexity constant. So in tabulation approach, we have observed that the current state calculation is dependent on the next two index values, which is I plus 1 and I plus 2. So instead of creating the whole array and returning the dp of 0 value, we can just use these two pointers itself, and then we can return the pointer which is pointing to the first index. So in this way we can remove the extra O of n space which is taking by creating this dp array, and with the help of these two pointers itself we can optimize our space complexity from O of n to O of 1. So let's understand how. The logic remains the same, but in here, instead of building the whole array, we are just using two pointers here. So again we'll start from n minus 1, and initially we'll take two pointers which is next 1 and next 2. So generally the next one is nothing but dp of I plus 1, which we have used in tabulation method, and next 2 is dp of I plus 2. So these two pointers would be initially 0 and 0, and we'll again follow the same process, which is starting from the last index, and we'll calculate according to a recurrence relation, and we'll move these pointers one step behind. So when we reach at the end, our next one pointer would be pointing to our first index, and we'll return this next one pointer which would store the maximum amount of money we can collect without alerting the police. So in this way we have optimized our space complexity from O of n to O of 1, and this method is called space optimization method. So the final time complexity of this approach is O of n, and the space complexity is O of 1. So let's quickly code this approach and let's submit. So here's the code for our space optimization method, where we'll take two pointers next one and next two, and we'll start from the last index of our nums array, and we'll calculate the maximum value, which is maximum of nums of I plus next two comma next one. And after calculating the current state value, we'll move our pointers one step behind, which is next two becomes next one and next one becomes the current value. And after finishing the whole loop, we'll return the next one pointer. So let's quickly run this code. It's working, so let's submit. So the final method also gives us successful submission. So this is the most and the best optimal solution for this given problem statement. So now let's learn something much more valuable than today's problem. So whenever you see a problem where at every index you have two choices, that is take it or skip it, and your future answer depends on the next few positions, there's a very high chance that it's a dynamic programming problem. So house robber is actually one of the most important patterns in DP. The same idea appears in the maximum sum of non-adjacent elements, as well as delete and earn, and several stock DP problems, and many more interview questions. So don't just memorize today's code, understand the pattern that will help you solve dozens of DP problems later. And that's it for today's video. Today we learned how to move from brute force recursion to memoization to bottom up tabulation, and finally space optimization. And that's exactly how you should approach dynamic programming problems in interviews. So if you found this explanation helpful, don't forget to like the video, comment if you solved it differently, or have any questions. So we are done with the third problem of the LeetCode 75 challenge. Share this with your friends who are preparing for placements or coding interviews. And most importantly, subscribe to the channel, because tomorrow we'll continue with another exciting problem from DP1D chapter, that is domino and domino tiling. Thank you so much for watching. I'll see you in the next video. Until then, keep coding, keep growing.